Hello, welcome to the Indian Institute of Chemistry. Our today's topic is elimination reaction. See, just like substitution reactions, elimination reactions also has three flavors: E1, E2 and E1CB. E1 is known as elimination unimolecular reaction, E2 is known as elimination bimolecular reaction, and E1CB is known as elimination unimolecular reaction via the formation of a conjugate base. These three flavors of the reaction has a common feature in them, that is, they give rise to an alkene. That is, its starting material should have a CC bonded skeleton. With this said, it is clear that CH3 leaving group, this one, a methyl containing leaving group, will never undergo an elimination reaction. For elimination reaction to undergo, the carbon should have a leaving group and the adjacent carbon should have a hydrogen. Okay, this is the basic structural feature or skeletal nature of a elimination reaction reactant. Okay, today we are going to discuss about the most introvert flavor of these three forms of elimination reactions. Yes, you are right, it is E1 reaction. E1 reaction is most sensitive reaction of them all. Why? Because E1 reaction occurs with the formation of a carbocation. Okay, then it might get you the fact that the stability of the carbocation should be able to predict whether the molecule will undergo E1 reaction or not. But here, not only that, a different aspect is also present, which is that if the carbon attached to a leaving group is 3 degree, then this will undergo E1 reaction under specific condition. The specific conditions are very important. And if the carbon which is attached to a leaving group is secondary, then it must be attached to a carbon which is tertiary in nature. So these two forms are very important for becoming a reactant in the E1 reaction. Okay, with that said, let us come to the mechanistic part of E1 reaction. See, E1 reaction is an unimolecular reaction. So it will be a two-step process. This will be a two-step process. Okay, the first step will be same as that we have seen in SN1, that is formation of a carbocation. Okay, the formation of a carbocation. The carbon having a leaving group, it is attached to a carbon having a hydrogen. Suppose this is the tertiary moiety or tertiary skeletal of a 3 degree alkyl group having a leaving group. Okay, now here the leaving group will leave this part and this will lead to the formation of a carbocation. Okay, with the liberation of leaving group. This is a slow step, as we have already known that breaking of a bond requires huge amount of energy, so the reaction rate is slow, and this is also being referred to as an RDS or rate determining step of the E1 reaction. This formation of carbocation via the breaking of the bond is very essential. If this carbon is 2 degree and it has a carbon here which can form a 3 degree or which is a 3 degree, then this hydrogen will migrate to this one and this carbon will get a positive charge here. So that will be the structural feature for a 2 degree carbon, as we have discussed earlier just right now. Okay, but the main thing is that E1 reaction, for this E1 reaction, rearrangement is very much important if 2 degree carbon leaving group bond is present. Okay, Now let us go to the second step. In the second step, we will see that abstraction of proton will happen. Abstraction of H plus will happen. Okay, sometimes this type of formation or this type of method is also known as proton transfer. Okay, this is also known, sometimes it is referred to as protons transfer. From the statement, it is clear that the proton is necessary and the proton must be adjacent to C plus. Okay, so what is happening here? This carbocation with hydrogen, and I am applying a base here which will abstract this hydrogen. This will come here and a CC bond will be formed. Okay, this is the main form of this reaction. Now we have already talked about the RDS step. The first step is the RDS step of this reaction. So what will be the kinetics of this reaction? Now we will talk about the kinetics of this reaction. The kinetics of this reaction will be very simple. Rate will be directly proportional to the concentration of the alkyl group having the leaving group. Okay, as we have seen that this is the only reactant molecule which is in the RDS, so this will be directly proportional to this, and rate is equals to K. If we remove this proportionality sign, then K into concentration of C, CH and leaving group. So this is the rate equation, and order of this reaction, order of the E1 reaction, okay, is equals to 1. Order of the reaction is 1 and it is unimolecular. Okay, understand? Now let us come to the stereochemistry part of this reaction. So what will be the stereochemistry of this reaction? The stereochemistry of this E1 reaction is very simple. That is, it does not follow any stereochemistry. E1 reactions, stereochemistry is nowhere to be found. Okay, so no stereochemistry is essential for E1 reaction. But there is a but. It sometimes tends to produce a product which has a greater substitution. Product with a greater substitution is favored. Okay, there is no requirement of stereochemistry, but sometimes we favor, the reaction favor the formation of a product with greater substitution. Okay, and also a formation where steric hindrance is minimum. So these two are the steric requirements, stereochemical requirements of the E1 reaction. Okay, so if there is a compound, suppose this is a compound CH3, C, CH2, CH3, here is a leaving group here, and suppose here is CH, CH3, CH3. Suppose this is the group which is undergoing the E1 reaction process. Then what will be the product? First of all, we will see that there is no stereochemistry because a carbocation formation will take place, and then the H plus, any of the H plus from any of the side can be abstracted by the base. Okay, but what is happening here? Here, if this hydrogen is getting abstracted, then a stable carbocation or a stable product, suppose this is CH2, CH3, okay, and C, CH3, CH3. If this hydrogen is being abstracted, then the double bond will be the most substituted. Okay, if this hydrogen is abstracted, then a substitution will be less, but if this hydrogen is abstracted, then substitution will be highest. So this will tend to give this product. And if I again consider what type of stereochemistry, steric hindrance should be minimum. If here in place of CH3 I give CH2 CH3. Then this CH2 CH3 should be here, CH2 CH3, it should be here. Okay, so this is a favored conformer. This is a favored conformer of a E1 reaction product. Understand? This sometimes may be referred to as E1 reaction. E1 reactions tends to form safe, or sometimes Z-safe is also written in some books, Z-safe product with trans geometry. So it is sometimes said that E1 reaction tends to form Z-safe or Z-safe product with trans geometry. Okay, this is the stereochemistry of this reaction. But actually what happens is that when this stereochemistry, CH2 CH3, here this is CH3, this is CH, here CH2 CH3, and here is CH3. This is what the carbocation was when this leaving group leaves. This carbocation, the base may abstract any of the hydrogen. The base may abstract this hydrogen, may abstract this hydrogen, or may abstract any of the hydrogen from this carbon. But it choose this hydrogen because here a double bond formation will make it more stable. A more substituted double bond is more stable than an unsubstituted double bond. We will learn about it in our upcoming series. Why is it so? Okay, but up to here you should know that this is the main thing that is happening in this elimination reaction. Okay, now let us come to the solvent specificity of E1 reaction. What should be the nature of the solvent for E1 reaction? It is very important. I have already told you it is an introvert reaction, and solvent specificity is very important for this type of reaction. Okay, first of all, let me draw the reaction coordinate for this type of reaction. This is the energy, the y-axis be the energy, and let the x-axis be the progress of reaction. Okay, now according to this, at first a carbocation formation will take place, then the product will form. This is the region where the carbocation formation takes place. Okay, so carbocation is a charged species. As you can see the energy profile diagram, you will see that the charge is concentrated on the carbon. Okay, if we use a high polar solvent, then the positive charge will be caged perfectly. If we use a high polar solvent, high polar means like water. If we use a polar solvent, highly polar solvent like water, then it will cage this carbocation very well. Okay, through its hydrogen dipole bonding, exactly the same. Okay, but if we use a solvent of less polarity like alcohol, then the charge on C+, can be spread over its adjacent carbons, which will ease the proton abstraction over nucleophilic attack on C+. Understand? If we use a low polar solvent like ROH, suppose I am using an alcohol, then this has a high polarity, this has a low polarity. The caging will occur less. The caging will occur less here. Okay, suppose this is oxygen, this is hydrogen, this is the lone pair on oxygen which is used to cage. Okay, but as it is alcohol and the polarity of alcohol is very low, so the caging will be very less. Okay, and the charge can be dispersed. This charge can be dispersed over the adjacent carbon. This dispersion of charge on the adjacent carbon makes this hydrogen more electropositive, makes this hydrogen more electropositive, or I can say that it gains a delta positive charge. This dispersion, which gives this hydrogen a delta positive charge, makes it acidic in nature. Okay, and this acidic hydrogen then can easily be abstracted by the base. Okay, and will lead to the formation of a double bond. Understand? This is the solvent specificity. Solvent specificity tells me directly that the solvent should be of low polarity, that is alcohol, or sometimes we can use DMSO or acetone, okay, so that the caging of this carbocation is not much enough so that only the stabilization of carbocation takes place. What will happen if we used water? If we have used water, then this caging would be perfect. Okay, the dipolar interaction would have been perfect, and the lone pair on oxygen would be perfectly caging this moiety, and this positive charge won't have dispersed to this carbon. And as the dispersion would have been not possible there, so the reaction would haven't occurred in the elimination form. It should have been directly as a substitution reaction. Okay, this is the solvent specificity. A point to be noted here that E1 reaction always competes with SN1 reaction. But E1 reaction can be favored if we just rise the temperature of the reaction or lower the polarity of the solvent to an extent that it is very less polar. Okay, so this is the main two factor which we should use. Now what we are using here? We are using a base here. This base should be a negatively charged entity with high affinity of H+. Okay, but its concentration should be very low. Okay, the use of base should be very much carefully be taken. Why? Because if we use a strong base, then we will end up in giving rise to a E2 reaction, which is not our main term. We will use a base of low strength. Okay, we will use a base of low strength. Thus, this low strength of the base will favor the elimination reaction, that is the E1 reaction. With that said, up to this, it is overall the E1 process. Hope the total concept about the process is clear. Okay, goodbye.